Hi, everyone. Welcome to the last meeting of GOCC for this academic year. Um, Today, we're really excited to have Patty Commins from University of Minnesota. Before we start, I just will remind us of our community statement. In short, it's that we're all learning, everyone has something to contribute, and no one has all the answers. Take it away, Patty.
All right. Well, yeah, thank you for very much for coming, and thank you also to all the organizers for putting on this seminar this year. It's been really cool. And if it's very nice to be back here. I think I spoke in it like 3 years ago with on a project that was joint work with Sarah Bronner and Vic Reiner that was like related to this project and kind of inspired a lot of the questions here. So I think it's nice to come back later on and have a few more answers for those questions. But this is all joint work with Ben Steinberg, who is at the CUNY Graduate Center and the City College of New York. So just as an outline, I'm going to spend like probably most of the talk just like kind of introducing left regular bands and these like algebras that are attached to them, because I think they're not like super well known always. So we'll go through a few examples. These are going to have like posets that are attached to them. And then we're going to look at some algebras that are attached to them and like a little bit about their representation theory. And then kind of where this work focuses on left regular bands that carry more symmetry. So I'll tell you a little bit why like one might want to look at these. And then I'll tell you some of what we did. So I'll kind of focus on like the answers for a specific subclass of LRBs. Okay, so just to get started, I'll define what left regular bands are, and I'll often call them LRBs. So if you hear LRBs, it's just shorthand for left regular bands. And these are a special type of semigroup. So a semigroup is a set that has some multiplication that's associative, and it doesn't even need to have an identity, let alone inverses. If it does have an identity, then it's called a monoid. And so left regular bands are like very special type of semigroup, and they're always going to be finite for us. And what makes a semigroup a left regular band is if it satisfies these two properties. First, every element needs to be idempotent. This is what makes it a band. And then we also need that xyx is equal to xy for all x and y. And this is like the left regular property. All right, so this is like a very specific definition. So you might wonder, like, why would we want to consider these semigroups? So I'll tell you a little bit about like why people have in the past. I think like the reason that kind of made them more popular is that they turned out to have some probabilistic applications and some connections to like Markov chains and different card shuffling algorithms. So first, Bidiger, Hanlon, and Rockmore, and then in works by Brown-Diaconis and Brown, people noticed that LRBs kind of carry several like Markov chains like within them, and you can use the like structure of the LRBs to evaluate the eigenvalues of these random walks. And it kind of united these like different Markov chains that seemed unrelated, but this gave them like a uniform way to compute their eigenvalues. And so this is kind of when they first, I think, became like popular. More recently, that people have been studying their representation theory, and I think like from my perspective, one reason to do this is that it's like I think it's kind of a very nice class to consider because it's quite rich. Like, you know, it's no longer are these algebras or are these LRBs semi-simple, but they're still very kind of doable, and you can still kind of write down everything you'd want. So it's like a nice class to try to gather information I feel like it's like the right level to consider. And this has been studied by a variety of people. And I think like the first place that LRBs appeared, it wasn't even here, it was earlier by Schutz and Berger, and he was considering them as generalized semilattices. So you can kind of think about them as some more general version of a semilattice, and I'll say more in a moment. And then finally, for this seminar, they kind of have a lot of connections to combinatorics, which is cool, and the combinatorics informs a lot of their structure. So I'll start out by giving you a few examples. So the first one that I mentioned were semilattices. So you could either do like joint semilattices or meet semilattices. We're going to stick with meet semilattices. And a meet semilattice is an LRB because, so in case you haven't seen it before, we say that the X wedge Y, this is like the meet. And this is the greatest lower bound for X and Y. And semilattices have the property that like there's a unique meet. And so like in a semilattice, if you meet an element with itself, you get itself back. And if you do this like left regular property, X meet X, you'll still just get X meet Y. So this is one example of an LRB. And a couple of things to note about this one. This one is very special in that the LRB is commutative. So X meet Y is always equal to Y meet X. And in fact, these are going to be the only commutative LRBs. Any commutative LRB can be shown to be isomorphic to a meet semilattice. And you might also notice that LRBs, or that these semilattices may not have an identity. So these aren't always going to be monoids, maybe just semigroups. For example, like in this semilattice, there's not going to be an identity. An identity would end up having to kind of be the top, like some maximal element in order to act like an identity for all the elements. Okay, like the second example, and this is the one that kind of people started to notice connections to probability with, are these face monoids of hyperplane arrangements. So a hyperplane arrangement is a collection of hyperplanes, which are just n-1 dimensional subspaces of some n-dimensional Euclidean space. So for example, like my drawing is a bit poor, but imagine you're in R3, then your hyperplanes are true planes, like two-dimensional planes, and here's a collection of 3 of them. And this is kind of a famous hyperplane arrangement called the braid arrangement, and that's the one where you have like pairs of coordinate equal for all coordinates xi, I is 1 through n. So these hyperplane arrangements have pieces called faces. And the way you get faces is by intersecting like half spaces and hyperplanes. So for example, here's a hyperplane arrangement with 3 hyperplanes, 1, 2, 3. And we can get a face by like choosing one of these spaces, either the hyperplane or half spaces for each hyperplane. So maybe for this first hyperplane, I'd pick this half space. For the second hyperplane, I'd pick this upper half space. And then for the third hyperplane, maybe I pick this, well, maybe I should pick the hyperplane itself. So maybe for this hyperplane, I'd pick like the hyperplane itself. Or oh wait, sorry. I'll pick the upper half space for this hyperplane as well. And then we get some like the intersection of all of them is this chamber here, and this is like one of the faces. And the faces are really kind of the pieces you'd expect of the hyperplane arrangement. Like this arrangement will have one zero-dimensional face. It will have 6 one-dimensional rays, and it will have 6 chambers. These are the two-dimensional faces. And so there's a way to form a left regular band from these faces. And the way to do it is this kind of strange multiplication where you nudge one face towards another. So say you have this face F and you want to multiply it by this face G. What you do is you like pick some point on F, some point on G, and you take an epsilon step from F towards G. And when you do that, you're going to end up in some potentially new face. Here we kind of step off the ray into this chamber. So this chamber here that I've highlighted is the face F times G. And you can notice that if we went the other direction, if I stepped off G towards F, I'd end up in this chamber here. So we get a different face, and this is a non-commutative LRB. Okay, so that's how you make it, and it takes a little bit of work, but you could convince yourself that it satisfies the two LRB properties, that every element is idempotent and xyx is equal to xy.
Patty, can I ask a
Yeah.
question on the previous example? Um, what would happen if we, instead of that last space, so in the gray, if we picked the other part of that, what would,
Uh, Good
yeah,
question. Yeah. So yeah, I was sweeping this under the rug of it. If you mean if I picked like this one here.
yes, that's it.
Yes, yeah. So sometimes if you get an empty face, if you get an empty set, then you ignore it. Then it doesn't give you a face. So you'll always
Okay,
either get
yes.
like an empty intersection or the intersection is a face.
Okay,
Yeah, that's
nice.
a good question though.
Nice. Thank you.
Yeah.
Oh, and on that next page, so the monoid specifically is the F times G and G times F, right? Like that, those are the two. Yeah,
Yeah,
that's
yeah,
that
that's how
I can do
the
that multiplication, right?
yeah, that's how the multiplication works. Yeah,
Okay,
and you're right to
yes.
point out I said monoid, and I should have you also check that this zero-dimensional face is going to be an identity element. So you
Yes.
this one really is a monoid.
Nice.
I have
Okay.
another I have another question.
Yeah.
So here you did the multiplication of something actually on a hyperplane and something actually on a hyperplane. Could you do like a quick example of like you take an actual chamber times one of the faces that's a hyperplane and like
Yeah,
how that works?
definitely. Yeah, that's a good question. Yeah, they're not as quite as interesting because if you take a chamber, so maybe we'll call this chamber C, and maybe you want to multiply it by C prime, this other chamber. With chambers, when you take epsilon steps from one towards the other, you still stay in your chamber, you don't leave it. So
Okay.
the chambers are kind of these weird special elements that like suck everyone to be a chamber. So yeah, like the C times C prime will be equal to C, and then here C prime times C will be equal to C prime.
Okay. Thank you.
Yeah, yeah. Other questions?
So is a product like always going to end up being a chamber here unless it's like something with itself?
So yeah, I guess this is a pretty small example, so it does look like this. Um,
Or like
Not
I guess one of
quite
the things is
so,
contained in the other, maybe?
yeah, it's like that. So yeah, if I did like this face times this face, so like if this is F, this is F prime, this is equal to F times F prime, like I wouldn't leave um the hyperplane. So yeah, it's not always going to be a chamber. And in bigger hyperplane arrangements, it get a lot gets a lot more interesting. But things do kind of in general like kind of get sucked into bigger like dimensional phases, and this like containment thing you mentioned is definitely plays a part. Yeah. Any other questions?
Can you repeat like what this product, this multiplication?
Yes. Yes, I can. And yeah, and I'm giving you kind of the like cheating definition that's not super rigorous. There is more rigorous ways to multiply them, but kind of the way it works like in pictorially is you if you want to multiply face F times face G, you pick a point on F and G. So here I've picked a point on F, picked a point on G, and you just take an epsilon step along the line between these two. So I'd start at F, take an epsilon step. I end up in this face, this two-dimensional face. So that chamber is F times G. Does that make sense?
Yeah, okay.
Okay, cool. Great. Okay, and then I'm going to show you one more example of an LRB that comes from the space of phylogenetic trees. So there's a phylogenetic entry for our purpose is going to be some tree whose leaves are labeled with the elements 1 through n, and they're going to have no vertex of degree 2. So I can draw out for you all of the phylogenetic 4 trees that look like this. And what's cool is that these phylogenetic entries can all be kind of seen to be connected by growing or contracting like internal edges. So for example, I can get from this tree to another by like growing and contracting this edge right here, right? And you can kind of think about that as a line, like over here, that edge has length 0. Over here, this edge has length 1. And maybe at some point in the middle, like, your edge is partially grown. It has length 1/2. So you can kind of think about these as like being morphed into each other continuously by adding lengths to the edges. And, this isn't the only growth that could happen. You could also grow like a different internal edge. So here, like we can grow along this axis by growing this edge, but we can also grow along this axis by growing the edge between 3, 4 and everybody else. And a point like along here would be assigning some length between 0 and 1 to this edge. And you can do like both simultaneously, and you kind of get this cube picture. So, okay, maybe you're looking at a tree who's like, you can pick 0 and 1 for either of these internal edges, and this gives you like a cube structure where you can pick an element between 0 and 1 for both. Dog graphs. Yeah, people do keep saying this, and I don't know if someone else has commented that they look like the like hot dog dogs. I think yeah.
Hi. May I ask a question, please?
Yes.
Are these trees do these trees have an orientation? Like, are they directed or something?
No, not directed. No, just leaves are labeled. Yeah. Yeah, so you can kind of grow and contract these edges, and they get all connected, and there's like these cubes that come into play. And so if you do this, like, connect all the trees in your space this way, you're going to get some space that turns out to be a cube complex, which you can think about as like a cube analog of simplicial complex, called the space of phylogenetic entries. So I can draw out like the whole picture for n is 4. I told you there were 4 phylogenetic 4 trees. So these are like the vertices of our space. And then you get like the edges by like growing and contracting internal edges. So here I'm kind of representing this one cube with a red edge by saying this consists of all the points whose lengths are in 0 and 1 here. And I can't really draw the whole space for any bigger n, but I can draw specific cubes. So for phylogenetic 6 trees, here's an example of a 2 cube within it. You know, basically a 2 cube is a phylogenetic entry where 2 of your internal edges are allowed to vary between 0 and 1. And you can kind of see its subcubes this way as well. So I told you there's like an LRB structure on these. And this comes from a theorem of Margolis, Saliola, and Steinberg, and also Bandel, Chapois, and Nauer that were proved independently, despite the dates. Actually, they like appeared around the same time on arXiv. And they both tell you that there's an LRB structure on the faces of any cat0 cube complex. And I won't tell you exactly how that works in general, but I can tell you how it looks like for trees. So the idea is that like each cube in our complex, we can represent as like a tree with colored edges, with some red edges that you can pick lengths for. So we need to figure out a rule to multiply one tree with red edges by another tree with red edges. And the way you do this is with something called splits of trees. So if I pick some internal edge of my tree, and cut it and like split it there, it's going to put my like vertices into 2 connected components, which gives me a subpartition into 2 pieces of the numbers 1 through n. And these splits kind of determine the multiplication. So the way it works is like the hyperplane arrangement, you're gonna, and kind of, instead of nudging one face towards another, we're gonna nudge one tree towards another. By like, we'll start with a tree, and then we'll consider every red edge and nudge it to look more like something in here, and I'll tell you what I mean by that. So for instance, I'll look at this red edge here. This has the split where 1 through 7 is together, but 8 through 12 is the other component. So I'd look to see if there's another edge with that same split here. But there is not. You can, check all the edges, and there's not going to be someone that has the same split. So to make it look more like the second tree, I'll trim that edge and contract it. Whereas like for this one, if I look at this red edge and cut it, I can look to see if there's a split in the second tree. And there is, it's right here, but it's no longer red, it's black. So I'll change it to black, which means like I'm no longer allowing my points to float between 0 and 1. The lengths are fixed to be 1 now. And similarly, like for this last red edge, there is a similar split, and it is still red, so I get to keep it as red here. So the multiplication is not very important for the talk or anything, but just to give you a sense that LRBs are often kind of nudging one element like towards another. Okay. And yeah, so I told you there were a lot of these in combinatorics, and we won't do any more of them. But if you're interested, you can kind of look at like these references of like Brown or Margolis, Saliola, Steinberg, and they explain a lot of LRBs associated to different combinatorial objects. Okay, so one thing that makes these LRBs so nice to work with is that they have posets associated to them. Like specifically 2 posets. One that's a little coarser is called the support semilattice. And this is going to be the poset of principal left ideals of your left regular band. So I just mean like you'll look at all the elements, the ideal generated by a specific element in your semigroup. You order these under inclusion. This turns out to be a meet semilattice. It's not very obvious that that's the fact, but it's true. And the second poset is a bit finer. So like here, two elements can give rise to the same ideal. So there's fewer elements in this poset than there are in the semigroup. But the semigroup poset will have one element for everybody in the semigroup, and you're ordered under this kind of funny relation, x is smaller than y if and only if yx equals x. So, oh,
Oh, yes, Patty, the B here is the band, right?
yeah, the
okay.
B here is the, so I'm kind of being sloppy and using B both for the poset and the band itself. Yeah. Yeah. Oh,
I was just saying thanks, don't worry.
oh, you're welcome. Okay, so yeah, you can get between these two in kind of the obvious way where you take an element to the ideal, then it generates. And again, we won't care like so much about the specific definitions of these posets. They have motivation in like monoid theory and semigroup theory. These appear. But if you're more interested in the combinatorics of the object, a lot of times these posets reflect that combinatorics very nicely. So say you're if in our simplest case we had like the semi-lattice L. It's not super interesting when you use the semi-lattice. All of the posets associated to it are still just L itself. But it gets a little bit more interesting when you deal with the noncommutative LRBs. So for the hyperplane arrangement, face monoid, your kind of coarser poset is this lattice of flats that you might have seen if you've worked with hyperplane arrangements before. And then your semigroup poset is actually related to Laura's comment about kind of how this multiplication depends a little bit on like whether faces are included in each other. So it's faces ordered under reverse inclusion. And this turns out to be the face poset of a certain polytope that's associated to the arrangement as well. And if we specialize to the braid arrangement in particular, this lattice of flats turns out to be isomorphic to the set partition lattice. And the zonotope that comes up for us is the permutahedron. So these might be familiar posets that you've worked with before. And for the tree LRB, this coarser poset has appears in a lot of different ways, but I think one of them that I don't know much about, but it seems like other people recognize more than the other ways I've seen it, is this face poset of the K is 2 tropical Grassmannian. And then the semigroup poset is just the face poset of the cube complex itself. Okay.
What was the ordering on the support semilattice?
Yeah, so the ordering is
Oh, under inclusion.
inclusion. Yeah, these principal ideals under inclusion. So yeah, there's some kind of I'm not actually telling you, the isomorphisms here, but they're not too surprising if like to write down. Yeah.
Okay.
Yeah, so these posets kind of allow us to define different classes of LRBs, and we're going to kind of focus in on one class today in particular. So one thing that will matter a bit to us are these contractions, which are certain subposets of your finer semigroup poset. These are just the elements whose like ideals are big enough. So you kind of pick one, you pick an ideal and you look at the elements whose generate an ideal, including that. And I'm going to give you this kind of strange definition that will become more motivated in a second. But if you look at all these contractions and the Hasse diagrams turn out to be connected as graphs, then we're going to call the LRB connected. And pretty much like all the LRBs you might care about are connected, and like the ones I showed you today are definitely connected. There are disconnected ones, but they're kind of not super interesting often. Okay, and the other thing that contractions will tell us is when an LRB is something called a CW LRB. So that's we'll say that an LRB is a CW LRB if its contractions are all face posets of regular CW complexes. So you might have like seen I said for the braid arrangement, the semigroup poset is the face poset of the permutahedron. And if you do like contractions, you still get CW complexes. And this is also going to be true for any cat0 cube complex. If you take these like contractions, you're going to get some connected cube complex. So there are a lot of LRBs, but not all of them are CW LRBs. So the ones that are important to us today are just like the real hyperplane arrangements and the cat0 cube complexes. These are going to belong to this class. Okay, questions before I get into the algebras of these? Okay, cool. So an LRB algebra is a ring that you get by like taking linear combinations of your LRB and extending the multiplication linearly. So it's a vector space, but it also has some multiplication. And we're going to work over a field, K, and sometimes we'll add some extra assumptions onto this field as well. And so the first thing you might be worried about is that, okay, our semigroups don't always have a 1, and we saw that there were some LRBs that didn't have an identity. But when you work with rings, you often want a 1. So that's where this idea of a connected LRB comes in. So it's possible that the LRB doesn't have a 1, but the algebra does. Like when you take different linear combinations, you get some identity element. And so the characterization of like what determines these types of LRBs is this definition of connected, which is quite nice. So you can kind of tell that the algebra of an LRB has a 1 if and only if, you know, it has this connected property. And we'll assume from now on all our LRBs are connected. So if you have a 1, then you might, you can think about like the algebra and consider what does the representation theory of this algebra look like. So I'll give like a crash course on representation theory of finite dimensional algebras, which will be probably like too fast if you haven't seen it before, but hopefully you can just give you can take away some of the big ideas of what one might be looking for. So we're also going to now add the assumption that our field is algebraically closed, just to make certain things a bit nicer. So when I say a representation of an algebra, this is the same thing as like a module over the algebra, or you can think about it as like a vector space that has an action by the algebra that satisfies certain linearity conditions. And we have like different adjectives to describe these modules. So the first is simple. These are kind of the smallest possible representations. They're often also called irreducible when you work with like group algebras. So we say a module is simple if it has no non-trivial submodules. And there's going to always be finitely many of these up to isomorphism. And a related but different notion are these indecomposable modules. So these are ones that like you can't, maybe they have some non-trivial submodules, but you can't break them apart into those pieces. Like you can't break them apart into a direct sum of smaller modules. And there are often, like in our situation, going to be infinitely many of these, but there are finitely many of them that are projective modules. So we'll talk about the like projective indecomposables because we can count them in a way. And an algebra is semi-simple if you can always break apart its modules into a direct sum of simple modules. So in this case, your simples and decomposables are the same and everything is quite nice. But this is going to be rare for LRB algebras and finite dimensional algebras in general. So some of the things we'll consider, like when we're looking at these algebras, are these data that are all in bijection. So there's certain idempotents that satisfy some nice properties, and these are going to biject with like the projective and decomposable modules, and you can specifically get them by looking at the ideal that that idempotent generates. And then these will biject with your simples by taking the top of those modules. So like we might kind of be, one thing we might be interested in is like, what does this data look like for an algebra? And then if you're dealing with specific modules of an algebra, you might try to understand its like smallest pieces. So unfortunately, like I said, most of the time our algebras aren't going to be semi-simple and we can't break them apart all the way, but you could always make some filtration of it by A modules, like a maximal filtration that can't be refined. And if you do that and you look at the like successive quotients, these are always going to be the same, maybe not the same order depending on your filtration, but always the same ones showing up with the same multiplicity. So these are going to be the composition factors. And this is kind of what we'll look at. It would be a little stronger if we could actually look at the filtration itself, but it's going to turn out the composition factors are a little, just like counting them is already a bit of a challenge for us. And so one way you can count the multiplicity of these factors is by just looking at the dimension of this vector space generated by the associated idempotent. And like special composition multiplicities that show up are the Cartan invariants. So these are when you look at the projective and decomposables that I mentioned. There's finitely many of them, and they biject with the simples. So you could like check for each of them, how many times does a certain simple appear? And you get, it's the same as this dimension here. And I'll maybe just point out that if you were at Victoria's talk last week, she was looking at this like Cartan matrix of these algebras to get her Coxeter matrix. And this is like the same notion. Okay, so don't feel like you need to remember all of that, but this is just kind of the ideas of what things we might be looking for. And specifically for LRB algebras, the data is quite nice. So it's rarely are we going to see a semi-simple algebra. This is only going to happen when we're in that special case of a meet semilattice, in which case the algebra is actually familiar. You might know this Mobius algebra is the algebra that comes up. But if you don't work with that, a meet semilattice, it'll be not semi-simple, but the data is pretty easy to access. And it's all in terms of elements of the coarser poset, this like support semilattice. So the members of any CF, or of any like the idempotents in any of those like nice families that I mentioned are going to biject with your projective and decomposable modules. And these will biject with your simple modules. And these are all going to be one-dimensional with super simple to write character formulas. So like they're very nice, the simples that come up. And I won't really go into any more detail than that in terms of like the LRB algebra representation theory, but if you're interested in it, there's a lot known about it. And a lot of it has been known kind of recently in this monograph by Margolis, Saliola, and Steinberg. And so they know things like the Cartan invariants that I mentioned. They also know a lot more like things about quivers, projective resolutions. And the thing that's really interesting for combinatorially about this is like most of their like descriptions and their proofs are done in terms of like the posets of these LRBs, and they're kind of done with this thing called poset topology. And the nicest answers are for these CW LRBs. So just to mention, like if when I say poset topology, what I mean is if you have a poset you can actually build a simplicial complex from this poset by like the vertices of your poset are going to be the vertices of your simplicial complex. And the simplices are going to biject with chains. So for example, this like chain of 4 elements should be thought of as this like this 3 simplex here. You know, this chain of 2 elements should be thought of as this 2 simplex, and each of these guys should be thought of as these 1 simplex. So when I say like the topology of a poset, I really mean the topology of like a simplicial complex that goes with it. And then you can think about like, you know, the typical things you might consider like cohomology or homology of these objects. And if you have a group that acts by poset automorphisms, you'll also act on these homology and cohomology groups. And this is kind of going to be like a tool that we'll use. Okay, so yeah, finally I can tell you a little bit about the LRBs with group actions on them. So I'm going to say an LRB has symmetry if there's some finite group that acts on it by semigroup automorphisms. And that just means that like G of B times B prime is G of B times G of B prime. So it respects the multiplication. And if this is true, then you can study this algebra that's inside of the semigroup algebra called the invariant subalgebra. And that's kind of going to be what we'll do for these algebras. So like one motivation here is that like a lot of these LRBs just have natural symmetry groups. So like the hyperplane arrangements, all of the reflection arrangements are going to carry actions by reflection groups, which will behave nicely with their LRBs. And like the phylogenetic trees, you can act on this cube complex by the symmetric group, you know, mapping like this cube to the one where you swap 3 and 6 on the vertices. So there's a lot that just have these symmetries in general. And there's also like some kind of interesting combinatorial algebras that pop up when you start to look at what the invariant subalgebras look like. So I think the like most famous example is Biddegair's theorem. And he looked at the invariant subalgebra for face monoid algebras for reflection arrangements. And when he did this, he saw that this algebra called Solomon's descent algebra showed up, which is quite nice. It's a quite nice combinatorial algebra. There's also a couple other algebras that show up as well. So the Montachi-Reutenauer algebra appears as an invariant subalgebra of another semigroup algebra that's not quite a left regular band, but very closely related. And then the random to top algebra can be shown to be isomorphic to the invariant subalgebra of another LRB. And so kind of like the hope of looking at LRBs with symmetry is that, okay, so there's these combinatorial algebras that pop up, and maybe since LRB representation theory is so nice, we can understand the representation theory of these combinatorial algebras by looking at them like inside of their bigger semigroup algebra. And this has been done like by a few people already. So it's been done by the descent for the descent algebra by a number of people. Maybe most notably, Saliola has done a lot to understand the descent algebra this way. And then there's been some recent work that has started to try to understand the structure of the Montachi-Reutenauer this way. So yeah, we're going to try to understand the like representation theory of the invariant subalgebra. Okay, could you say anything about why the first two are anti-isomorphisms, but yours is an isomorphism? Yeah, that's a good question. I guess one thing that I'll say here, so anti-isomorphism is like the isomorphism reverses the multiplication. So one thing about here is this algebra turns out to be commutative. So it could be, Trevor, that like maybe it doesn't act, this is also, I guess, anti-isomorphic. That's a good question. But yeah, this one turns out to be, it doesn't matter which way you multiply. Okay, so one things that you might want to look at are what is the structure of the invariant subalgebra itself? Like when is it semi-simple? When is it commutative? And if it's not semi-simple, what is these data of the Cartan invariants? Like what does this matrix look like? And then you can also look at some external representations that I think for time I will suppress. We will kind of ignore this. Okay, so maybe I've mentioned a couple times this descent algebra. And so just to give you a picture of what it looks like in type A, so for the symmetric group, this is a subalgebra of the symmetric group. And the idea is you look at like all the sums of elements who have the same descent set. And it turns out that when you multiply like two of these sums, you're going to get a linear combination of other sums of this form. And this is going to be closed under multiplication and form an algebra. So when I say descent algebra, this is really what I mean. And to kind of look at like what the answers look like for this algebra, we can check, okay, is it semi-simple? It turns out it's not semi-simple, and this was known before, all of these were known before viewing it within the face semigroup algebra. It's not commutative. And its Cartan invariants, this like matrix I mentioned, these are known, and these are very quite nice and combinatorial. So the simples and projectives are going to be indexed by partitions. And so you're looking at a matrix that's like partitions by partitions. And to find the mu lambda entry, you'll count some certain compositions that rearrange to your partition who satisfy this condition that I won't get into, but has something to do with Linden words that have like a Linden word type of lambda. So like the invariant subalgebras there's several like things about them that kind of come free from the semigroup algebras themselves. So now we're going to, in addition to saying it's an algebraically closed field, add the assumption that our characteristic doesn't divide the order of the group. And if you have these properties, then it's like kind of straightforward to find like what the idempotents look like, and then use these to get what the projective and decomposables look like, and what the simples do. And these are all still one dimension, and the simples are still one-dimensional modules. But we might wonder, okay, like when is it going to be semi-simple and when is it going to be commutative? And with Ben, one thing we did is kind of characterize this in terms of like the orbits of the two posets. So we said it's equivalent to check if the number of orbits of both of your posets agree. If that's true, then it turns out that your invariant subalgebra is semi-simple, and it's also commutative, and these are all kind of equivalent. So for the ones I've showed you today, the like braid arrangement face monoid, this is anti-isomorphic to the descent algebra, which has this dimension. And we saw that its support semi-lattice was like the subpartition lattice. And there will be one orbit for every integer partition there. So these guys are different numbers. They don't agree most of the time. So it's not going to be semi-simple or commutative, which matches what we know about the descent algebra. And you can do the same kind of computation for the tree LRB as well. But I'll point out that this does like recover work with Vic and Sarah, where like we found that this random to top algebra that showed up that Trevor asked about, we saw it was commutative and it was semi-simple. And this turns out to be like straightforward to check through this proposition, just the orbits of both have the same number. Okay, so to check like what we've answered so far is we've kind of decided like when it's semi-simple and when it's commutative. And I said we will ignore these for now. So one thing that's left is, okay, well, what do the Cartan invariants look like for these invariant subalgebras? And it turns out like one way to understand them is to look at these funny spaces called invariant Pierce decompositions. And these are spaces where you have an idempotent, one of these special idempotents on either side. And it's helpful to understand their G representation structure. And so we'll ignore this part. But to find the Cartan invariants, like to find out this data, the Cartan invariants, all you have to do is check for each of these invariant Pierce decompositions, how many times the trivial representation appears as a summand. So that's basically what we did is we looked at the G representation structure of these for like all different types of LRBs. The like braid arrangement is like a project I had done before and had looked at like these invariant Pierce decompositions and shown that these can be used to recover the Cartan invariance of the descent algebra. But with Ben, we were focused on kind of some more general classes. And the class that I just wanted to flash to you today, what we looked at were these CW LRBs. So these LRBs that had these regular CW complexes connected to them. So the idea is like the braid arrangement was an example of this. We said hyperplane LRBs were CW LRBs. So we were trying to see, can we generalize like a theorem like this to more general LRBs? And the very useful tool in like understanding these Pierce decompositions was poset topology. We were trying to, it turns out to be the same to like look at these spaces as it is to consider the representations on like the topology of certain open intervals in your poset. So for instance, like in the partition lattice, this would be like if your lambda was 4, 2 and your mu was 2, 2, 1, 1, 1, you'd be looking at the different intervals like this and trying to understand the representations on these like open intervals. And what we did was we generalized this to CW LRBs. So we showed that, okay, for a CW LRB, you can do the same thing where you have this invariant Pierce decomposition. You look at intervals in your support semilattice. And the thing that was really tricky here was to find the correct twists. So it's not true, like if you take away these, this is not going to be, this won't respect like the G action, this isomorphism. So we had to spend a lot of time trying to figure out what these twists look like. And eventually we were worried they didn't exist. They do exist, and we have them in terms of like also poset topology. And one cool thing is that like one specific type of CW LRB is cat0 cube complexes. And for those, the Pierce decompositions simplify very nicely into permutation representations. So like here using the like poset topology interpretation, it's not hard to show that this is a permutation representation, specifically of like these coset representations. And because it's a permutation representation, if you want to like count the amount of times the trivial shows up, it's quite nice because of that. And that allows us to get our Cartan invariants quite easily. So we can get the Cartan matrix just by counting different orbits of intervals in our lattice. But yes, sorry that this has gone over, but thank you very much for listening. And this, I'm happy to have any questions you might have.
Thanks so much, Patty. This was great. Any questions? I can.
You mentioned at the start that these are related to like Markov chains and probability. Could you say a little more about that?
Yes, I could. Yeah. So, yeah, let me try to find a picture to demonstrate this on. Okay, so, this here is like the braid arrangement, and like its faces are turn out to be indexed by these like ordered set partitions where you have like coordinates in order. And in particular, its chambers can be thought of as permutations. So like, this permutation is 2, 1, 3. This is 1, 2, 3, 1, 3, 2, and so on. So you can think about like the chambers as being like card decks, if you want, like different orderings of the card decks. And we saw that the chambers like kind of sucked everything into them. Like if you multiply a chamber times something else, you stay in that chamber. But what's maybe a little less obvious is that if you multiply something times a chamber, you end up in another chamber. So the chambers like suck everything into it. So because of this, you can kind of think about like any element of your face algebra is going to act on your chambers, like act on the set of chambers. That's going to be closed under the multiplication. So any element is kind of a random walk on the chambers if you weight the elements so that the coefficients are probability measure. So that's kind of how this came up. Like you can pick different elements of the face algebra that will act on your chambers or these permutations, like these Markov chains that have shown up in other places, like Riffel-Scheffling is one, random to top is another. Like the Setlin library more generally is like one that has shown up as well.
Patty, I have another question. So you mentioned this, right, when we were talking about poset topology, right, we are thinking of extending that action to the homology and cohomology groups. Is there anything we can say about the cohomology or homology groups for this? Like, are they interesting groups in some way, or?
Yeah, that's a good question. Yeah, so I mean, one thing for CW-LRBs, like these intervals in the support semilattice, these posets that will come up, they're always going to be a wedge of spheres of the same dimension.
Okay.
So they're like the representation will kind of be like concentrated in one dimension. And yeah, some interesting ones have shown up. So like in the braid arrangement case, these are kind of related to like the Lie representations and the higher Lie representations. In like other cases, you might see like the derangement representation has come up, or yeah, so yeah, sometimes you get ones that you might recognize, I guess.
Okay, yeah.
Yeah, they often like for nice LRBs, like the ones with these complexes connected to them, you get like spheres.
Okay, nice. Nice. Thanks. Okay, if there are no questions, well, let's thank Patty again for a great talk.
Thank you. Thank you for
Yeah.
having me. Yeah.
Yeah, totally. Thanks, Patty. Oh, and I should stop.